So, welcome back to Code-Free IoT. This is Raspberry Rudy, and on this video, we're going to jump into the basic concepts of interfacing, and that will really set you up to understand how to hook up things to the Raspberry Pi safely and properly and get good results right off the bat. And in this series of tutorials, we're going to be using Node-RED running on the Raspberry Pi. So why Node-RED, you might ask? Well, you can build things faster and test them faster. There's lots of online examples, libraries, and support. All the nodes are standardized for everybody. It'll give you a high probability of fast success, and your projects are reusable and expandable. The node library is very large and it's growing. It's very well supported. The software is also expandable using JavaScript, HTML, or SVG. And your projects, called flows, are easily shareable with others. So there's lots of cool advantages to Node-RED. So which Raspberry Pi is right for you? Well, I recommend you start with a 3B+. I think it's got the best bang for the buck. Now, you can upgrade to a Raspberry 4 with the best performance, especially a lot more RAM and some more processor performance, but it is somewhat more expensive. A cool alternative going the other way is a Raspberry Pi Zero W, which is great for dedicated or portable projects. It also, the W means it also has Wi-Fi. Raspberry Pi Zero 1.3 is the predecessor. It has no Wi-Fi, but you can add your own with a USB Wi-Fi dongle pretty easily. And the new Raspberry Pi Nano is great for low-power IoT projects, but it has a different interface and it's not quite as versatile. So this series of videos is going to focus on using the Raspberry Pi 3B+. So let's take a look at the Raspberry Pi 3B+, the most popular model out there. We start with the GPIO bus. It's a 40-pin total 2x20 header, and we'll look into more of that in a little bit. We've also got 4 USB 2.0 ports. We have an Ethernet port. We have a composite video and stereo audio output port. This is the ribbon cable connector for a Raspberry Pi camera. This is the HDMI standard size connector. This is the micro USB power input port. This is a ribbon cable connector for the Raspberry Pi displays that you can get. And under the board, pushed in on this side with the gold fingers facing the PCB, is where you insert your micro SD card. This is the main Broadcom processor, and this is another chip. I think it's memory and some other functions there. So that's the Raspberry Pi. So now let's take a look at some of the recommended hardware to get you going. So the first thing you're going to want to get is what's called a Pi cobbler. That's this T-shaped PC board that plugs into a standard solderless breadboard and connects to the Raspberry Pi using this cable. And you want to be very careful on how you plug it in, get the pins aligned, and get the orientation correct so that pin 1, which is a square pad on the circuit board, the other pads are circular, matches up with pin 1 square pad on this circuit board here. The next thing you want is a small power pack, at least a 1 amp. 2 amp is even better if you're driving some other electronics. The next thing is a micro SD card. I recommend 32 gigabit. It's not much more money than a 16 gigabit. I recommend you download the GPIO Header graphic or data sheet so that you can see that. We'll go into that here a little bit more in a bit. And finally, a great starter kit. You can get, this is a Freenove basic starter kit. It's got the Pi cobbler and ribbon cable connector. It's got some jumpers, LEDs, switches, buttons, lights, buzzers. It has a little resistor color decoder card. And it's got several different versions of resistors here, and of course a solderless breadboard. Pretty much everything you need to get started. Now, here is a much more complete starter kit with a lot more stuff. More LEDs, you've got keypads, you've got chips, you've got motors, sensors, a range finder, a motion detector, joystick, potentiometer, a whole bunch of nice stuff in here. Again, a Freenove kit. I have nothing to do with Freenove. I just know that you can find it on Amazon for a pretty reasonable price. About the same as what you could buy this stuff for individually. So it's a all-in-one kit. So I highly recommend it if you're going to move on with the Raspberry Pi. So let's talk about some basic interfacing concepts. First thing we want to talk about are voltages and currents. Voltages are like water pressure and currents are like water flow. And resistance is a little bit like the size of the pipe. The smaller the pipe, the more resistance, the less flow for a given voltage. And if you open up the pipe real wide and have a lot of flow, it can probably reduce your water pressure. In fact, it will reduce your water pressure. The same thing happens in electric circuits. And so we'll be talking about volts, amperes, and ohms. But very often we'll be talking about millivolts, milliamps, and kiloohms, k-ohms, or even megohms, millions of ohms. And milli means 1,000ths, kilo is 1,000, and mega is 1 million. Now we'll only be using digital DC circuits for interfacing. Won't be using alternating circuits like you use for power at home. These are DC circuits with constant flow, constant voltage, and are usually turned on or off for digital. Let's talk for a moment about devices and loads. Every device has a power limit. If you give it too much power, it'll overheat and it'll break. Usually a connection inside will break first, or the device itself will melt and break down. So in order to limit the amount of power that is allowed to flow through the device, we use a resistor that's used for current limiting, hence the name current limiting resistor. It's just like every other resistor, it's just what we use it for. That's why we call it current limiting. And what this does is it limits the amount of current flow. And as you'll see later on, there's a way to calculate how much power and therefore how much heat is dissipated by the device when that current flows. So you have to be very cognizant. That's one of the first ways to prevent breaking your electronic devices, is knowing what the power and heat dissipation capabilities of the device are and give it the appropriate voltage and current. You can't over voltage it because then you can short it out. You don't want to under voltage it because then it probably won't work. So then the next thing is we'll take a look at the GPIO header in terms of power, digital pins, and buses. We'll take a look at GPIO pin basics in terms of the signals on it, tri-states, pull-ups, pull-downs, and active logic. And finally, we'll take a brief look at the difference between analog circuits, digital logic, and pulse width modulation. So let's take a look at the Raspberry Pi GPIO header. So the first thing you want to notice is that it's 2x20 format. Now, the first Raspberry Pis had only the top 26 pins, but now all new Raspberry Pis have a total of 40 pins. Now, realize that these are the pin numbers here, and they go from pin 1, which is the only pin that is a square solder pad, and that's an industry standard across all of electronics. Pin 1 is a square pad, and they go all the way down to pin 40. That's different than the logical GPIO, general purpose input output port number. That's the logical name of that pin or the function of the pin. So don't get those two confused. So that's 3.3 volts for devices that need to be powered by 3.3 volts. The two red pins are your 5 volts, sometimes known as VCC. The two Blue pins are your I2C bus. And this one is the serial data, this one is serial clock. These orange pins are what's called a UART. The old days was an RS-232 port, and UART stands for Universal Asynchronous Receive Transmit. And one pin is transmit, one pin is receive. And you can use a cable that'll adapt that to USB to be able to send and receive things between the USB port on your computer and these pins directly without having to go through the USB port on the Raspberry Pi itself. And there's nodes that lets you get that data in and out directly from the Raspberry Pi in Node-RED. The next group is the magenta group here. These are SPI, serial peripheral interfaces, not to be confused with your conventional traditional serial port. And that works in a special way, and that's beyond the scope of these videos right now. These two yellow pins are associated with the I2C pins, and in certain circumstances, they use a memory called electrically erasable programmable read-only memory. And it configures all the devices on the I2C bus and loads up the registers of those devices automatically. But we won't be using those in these videos. And last but not least, all these green pins that you see here. Green pins, lots of green pins. And those are all the general purpose I/O pins, GPIO. And they're numbered uniquely. So in some of the nodes in Node-RED, you'll notice that you can either define it by the pin number or by the GPIO port number. So that's how we're going to distinguish these port numbers versus pin numbers. So that's pretty much a quick overview of the GPIO header. So let's take a look at resistor color codes. This is how you know what value resistor you have that you want to use to select how much current is flowing through your device. And we're going to look at the most common type of resistor, which is a 4-striper. The first 3 stripes give you the value, and the 4th stripe, usually silver or gold, tells you the tolerance or how precisely held the value is on those first 3 stripe numbers. And so the first 2 are the characteristic numbers, okay? So it might be red, which would be the value 22. The 3rd stripe is the multiplier, and that's the power of 10. And what that does is it shifts the decimal point to the right, okay? So it's 22, red would be 22 times 10 to the 2, or 100. That would be 2200 ohms, or 2.2 k ohms. A orange red would be 33 times 10 to the 2, or 3300 ohms, or 3.3 k ohms. And it goes on like that. If you want the more common values, here are the most common values for the first 2 stripes in terms of the multiplier of the power of 10, the 3rd stripe. So a brown, black, brown would be a 10 times 10, or 100 ohm. A 1k ohm would be a brown, black, red. So that it would be a 10 times 10 to the 2, or 100. So 10 times 100 is 1,000. That's 1k. A 10k would be a brown, black, orange. So it would be 10 times 10 to the 3, or 10 times 1,000, which is 10k ohms. So that's how resistor color codes work. So now let's talk a little bit about Ohm's law and calculating current, power, and energy. Couple laws are voltage is I times R, current times resistance. Or in another format, we can say that resistance is voltage over the current, which basically means if I have a higher voltage, okay, I need a higher resistance in order to hold that same current, okay? These two equations are equivalent. So if my voltage is 3.3 volts from a GPIO pin and the resistor is a 330 ohm resistor, then I divide 330 into 3.3 and I get 10 thousandths of an amp or 10 milliamps. Okay? If I'm using 5 volts and I'm using that same resistor, then notice I'm getting 15 milliamps. Okay? Proportionately more milliamps because the voltage is higher. Now the power rating for the device is voltage times current. And if you plug in this equation for V and replace V with I times R, you get I times R, which is I squared times R. The current squared times the resistance is the power. So if the voltage is 3.3 volts and we have 10 milliamps current, then we have 33 milliwatts, 33 thousandths of a watt of power dissipation. Not a lot of power, not a lot of heat, pretty well controlled. The last thing I want to talk about is energy. Energy is watts times time. So that's watt hours, for example. At home, your power meter runs in watt hours or even kilowatt hours typically. And that's power times time. And that's the total energy. If we run a 3.3 volt device at 10 milliamps for 1 hour, we get 33 milliwatt hours of energy consumed, just like calculating your home kilowatt hours on your home energy meter. So now let's talk about active high versus active low. This is the relative logic that we're going to use when we consider whether a pin is on or off, high or low, 1 or 0, active or inactive. Okay, so active high means I'm going to activate that pin only when the pin is at 5 volts or a 1 state as opposed to a 0 state, and to keep it, when I'm not driving it, to keep it pulled down to the 0 state by default. So default state is 0 and I have to pull it up with a signal from the Raspberry Pi. I use typically a 10K ohm resistor to pull that pin down and kind of hold it anchored down to the ground so it doesn't flop around. And we'll see why in a minute. Voltage is provided to the device when the logic is true or high or 1. And then current will flow from the pin through the device to the ground. That's how you wire an active high pin. Active low works the opposite way. We pull it up with a 10K resistor to hold it at the high or 1 or logical true state by default, and then the signal is provided by the Raspberry Pi or the device that pulls it down to ground, okay, so that when the logic is false or low, all right, then, or 0, current flows and it goes from the voltage source through the device to the ground. So I'm pulling the pin low. That activates the device when I pull it low, hence the name active low. So that's the distinction between active high and active low. So this is really more of a logical paradigm, a logical construct, as opposed to whether that pin is high or low. Let's take a look at logic states now. I said before that a pin that wasn't pulled high or low might be flopping around, and that's what's called tri-state. The pin is in indeterminate position. It's neither high nor low. It's not true or false. It's not on or off. And that means it's somewhere less than 2/3 of the normal voltage on the bus, but it's greater than 1/3 the voltage. So it's in kind of the intermediate indeterminate state. That's why we need very often a pull-up or a pull-down resistor to set the default state of that pin. We can also do that when we send a signal out on that pin. We can have a software pull-up or pull-down that pulls that logic from the Raspberry Pi side, pulls that pin by default high or low, waiting to be pulled in the opposite direction. A high state is when the voltage on that pin is greater than 2/3 typically of the voltage. So it would be 2/3 of 3 or 5 volts. In other words, somewhere around 2.2 volts all the way up to maybe about 3.5 volts here. And low state is when it's less than 1/3 of the voltage, VCC, which could be 3 or 5 volts. And it's usually very close to zero when it's in a low state. Then there's one more, a little bit of an advanced concept I want you to understand, and that's impedance. And that is a more general term with respect to resistance. And it's kind of a resistance that goes beyond the resistance of DC devices that are limiting direct current steady flow to limiting the flow of any kind of a signal, wiggling signal, steady signal, what have you. And the reason I want to talk about impedance is very important because we deal with this all the time. Impedance comes in two forms. High impedance devices are things that are typically driven by voltage, okay, voltage controlled devices. Things like transistors, logic, computer inputs, okay? And what they have is they have a high resistance, typically thousands of ohms, and that keeps the current low and keeps the voltage from being sagged or pulled down because the device is being driven by the voltage level. And so we don't want to put too much of a strain or a load on that voltage by sucking a lot of current and pulling it down. So therefore we introduce or we present a high impedance to that device. And so a lot of logic devices and computers are going to be high impedance devices. Now there's also current-driven devices that have a low impedance to current. They are happy to be driven by more current. And those things are sometimes computer outputs to things like LEDs, speakers, solenoids, and motors. Especially speakers, solenoids, and motors. For example, speakers you'll often see rated as 4 ohm or 8 ohm. Well, if I hooked up a 4 ohm speaker to a 5 volt battery, I would get 1.5 amperes of current through there, and it would make a loud popping sound. So, and I would pull my battery down pretty quickly. So I need a lot of drive to do that, and that's why you'll see a lot of solenoids and motors need special driver circuitry in order to drive that current through those devices and make them function. So they'll typically be at a few ohms, as I said, like speakers at 4 or 8 ohms, and that allows the current to flow to drive these more current-hungry devices. So that's a little bit like, impedance is a little bit like matching the gear ratio on your 10-speed bicycle. If you are going up a hill in 10th gear, you're going to work real hard and you're not going to go very fast and you're going to be tired real soon. If you are in first gear going down a hill, you're going to be pedaling like crazy and you're not going to be able to go any faster. You won't even keep up with it. So to match that up, you need the right gear based on how steep uphill or downhill you're going in terms of the resistance or impedance that you've got, and that's impedance matching. So there's an example of impedance matching a device to the drive, or your feet in this case. So the last thing I want to touch on in this video is the difference between analog, digital, and pulse width modulation signals. Here's a typical analog signal, and you see it's wiggling all over the place in terms of the value of the signal. That value could be voltage, could be current, could be a number of things. But it changes smoothly and continuously. This could be sound, this could be radio waves, it could be almost any kind of a continuous signal that's flowing over the air or through wires or what have you. Digital signals, however, are either 1 or 0, 0 or 1. And they happen with a leading edge and a falling edge as the signal progresses through time. And so this is a typical random digital signal. And lastly, pulse width modulation. Here you have 5 examples of pulse width modulation, so that the on state is 5, the off state is 0 volts. And you see that it switches between on and off for different amounts of time. And the amount of time it's on is called a duty cycle. So here, 1/4 or 25% of the time from the rising edge, leading edge, to the leading edge of the next cycle, it is on. Here it's 50% duty cycle, 75%, and here is 100% duty cycle or on continuously. And if you smooth this out with the device, the average amount of power, which is the blue line here, goes up as you increase the duty cycle. It's on for longer, so the amount of time you're applying power every pulse, the more average power you're delivering to the device. So this is how we'll be controlling a number of devices, as you'll see later on, such as LEDs or other things that can be controlled by pulse width modulation. This is how you control, by the way, speed control on a lot of devices like drills. A drill speed control is typically done with pulse width modulation, delivering power for only short bursts of time. So that wraps it up for basics of interfacing. Some deeper dives I recommend is to play around with Ohm's law calculations. Take a look at the voltage, current, and power specifications of devices like LEDs, buzzers, or any other small electronic devices you can find, motors, switches, whatever, and do some Ohm's law calculations and see if you can get a handle on the kind of voltage and use when you do that. And you should get familiar with the kinds of typical voltages that are needed to drive that device based on the currents that you want. And then finally, I recommend you take a look and study basic DC circuit schematics, from batteries or voltage sources to resistors to switches to activated devices like light bulbs and such like that. Take a look at schematics and you'll learn a lot, and this will really help set you up to really do a lot of things with interfacing. So to wrap up, please add your comments below and make some suggestions of new topics. I'd love to hear back from you of what kind of things you're either having problems with or you'd like to see solved or put together, and we'll try to build some videos along those lines in the future. And of course, click the like icon, hit the subscribe button, and click on the bell icon to be notified of future videos. So this is Raspberry Rudy saying good luck to you, and I hope you learned a lot. Study up, and look forward to seeing you in the next video. Bye-bye.